Okay, in continuation to the first lecture where we have introduced about this course, so we have defined in the previous class what is a signal and what is basically a system. So signal is nothing but a source of information, or mathematically it is a function of one or more independent variables. Okay, and the independent variables is mostly time when you say it is electrical signal. Okay, and in this course we mostly concentrate on one-dimensional signals only. Okay, that it is a function of one variable only, that is time. And then we have a system. So system is basically a physical device which is used to process a signal. Okay, and by processing you try to extract some information which is embedded in this signal, right? And we have two different systems for a continuous time system if the input is continuous time, and if the input is a discrete signal you will have a discrete time system for that. Okay, so this is a physical device, but say when you say discrete time systems, we generally process this continuous time system, although the signal is continuous in time, but we prefer to process this signal using a discrete time system. The reason is that when you use a discrete time system, you have a flexibility here that either you can implement this system using hardware or you can have a software part also. But in continuous time systems, you have only hardware. There is no counterpart in the software domain. Okay. So when you study in the higher courses like digital electronics, you study the digital devices, flip-flops, logic gates, resistors, and multiplexers, and so on. So this discrete system or a digital system, you can say, this can be designed using the digital components in the form of a hardware, or it can be simply a microprocessor. Okay, so in the microprocessor you write some code in the processor, you have a discrete input signal, it will process it and you will get the output. Okay, so if it is a software implementation, you have a flexibility that you can simply change the code, and by changing the code you can make this system in a different way. Okay, but in case of continuous time systems, or you generally say in analog systems, if you have a hardware or a circuit for that, and if you want to design any system you have to change the whole circuit, then you have to test it, and then you have to implement it. Okay, so there are many other advantages of discrete systems over analog systems, but this is a basic fundamental advantage why we go for discrete systems. See, in the classification of signals, we have categorized one thing, that was continuous and discrete time. Continuous time and discrete time signals. We denote continuous time signal with xt, we denote discrete with x of n. So t here in this case is continuous, n in this case is discrete. It means the signal information is available only at particular instance of time. And even when this signal, if this signal is converted from a continuous time signal using the sampling process, in that case we have lost the time information. It is just a sequence of numbers, nothing else. Okay, another important classification in signals is analog and digital. Okay, analog signal and digital signals. Now when you classify the signals based on analog and digital, we basically look at the amplitude axis, not at the time axis. Okay, so I take two signals here, one is x2t and one is suppose x1t. Okay, this has a variation like this, and this signal maybe has a variation like this. If you look at the time axis, both are continuous time signals. But if you look at the amplitude axis, the amplitude of this signal is continuously changing with time. Okay, it can take any value. The amplitude can take any random value. This is what is called as analog signal. In this case, the amplitude is fixed to two levels only, either as this level or at this level. So the voltage, if it is a voltage may be supposed at level 5 or level this is supposed 2. So either it can be 5 volt or 2 volt. This becomes a digital signal. Okay. And it is not necessary that it should take only 2 levels. It can take 4 levels, it can take 8 levels, it can take 100 levels. No issues. But the number of levels has to be fixed. It cannot take any random value. This is what is a digital signal. Okay. Similar in the discrete domain, if you see in the discrete time xn, you have one signal like this. Okay. And another signal, suppose I plot like this. This is one value, this another, then this value, then this, maybe like this. Again, in this case, the sample values, they are fixed to just two values, two levels. Suppose this is 2, this is 1. So either the signal value is 1 or it is 2, 1 or 2. Okay, this is again a digital signal. So this is digital signal, continuous time. This is continuous time analog signal. This is discrete time analog signal, because see, in this case your time is discrete in nature, but the amplitude is not discretized. In fact, it is again continuous. Amplitude is again continuous and it can take any value. So this is again analog signal. This is a digital signal and also a discrete time signal. Okay, this is what basically we use when you use a discrete time systems or a digital, or in DSP we use this type of signals. Okay, so in that case what we do, the signal that we actually have is like this, x1t, a continuous time analog signal. So when you sample it, it becomes a signal like this. It becomes a discrete time signal, not a digital signal. And then after sampling, we use another process that is called as quantization. So using quantization, what we do, we now discretize the amplitude axis. Means we divide this amplitude range into certain fixed number of levels. Okay, and at any instant of time, this signal amplitude, it can take only one of those levels. Okay, suppose we have 16 levels. Okay, that means if this is 0, this is suppose 15. Okay, so at this time, at n is equal to 1, this is the signal amplitude, and if it is exactly lying at the level, okay, this is its value, it will not be quantized. At n is equal to 2, suppose this is the signal amplitude, but it is not equal to a predefined level, so we round it to the nearest value. This is what is quantization. So finally you get a signal, the quantized signal, in which time is discretized as well as amplitude is discretized. Now all these samples, they will have their amplitude values which are from a set of predefined levels. Okay, and then we finally convert that this quantized signal into a binary signal using a coder. So if it is suppose a 4-bit coder, it means each level is represented by 4 bits. So you can have storage power 4, that is 16 levels. So if it is level 0, voltage 0, it will be represented by 0 0 0 0, then 0 0 0 1 2 3 4, then finally 1 1 1. It means output of that coder will be nothing but a series of binary numbers. For every sample you get a 4-bit code. Okay, and then this code basically goes into a digital signal processing system, and that processes it either in the form of a hardware or software, and you get the output. Okay, so analog to digital converter in that case becomes a important interface. If you want to process analog signal using a digital system, you need a to D converter. So you have XT, which is analog. You have an interfacing device, which is a to D converter, and then you have a DSP system. And output of the DSP, it is digital signal. If you want to convert back into the analog, you can use a digital to analog converter. You will get a output in the analog form. Okay, so this is a block diagram how you can process analog signal using a digital system. But there is an option whether you want to process the analog signal using the analog signal processing, or you want to process analog signal using a digital signal processing. So but we prefer DSP over analog signal processing for so many reasons. One of the reasons is the flexibility in the implementation. Okay, so this is another important classification of signals based on the amplitude values, whether it is analog or a digital value. Okay, so many times students get confused that continuous time signal is analog signal or discrete signal is a digital signal. Okay, so but it is not the case. This is based on the time axis, this is based on the amplitude axis, this classification. Okay, so you have to keep that in mind. So these two are important classifications: continuous and discrete time, analog and digital signals. Then you can have other classifications also, like we have in the last class I have told you the signal may be periodic and aperiodic. So if it is periodic, xt is periodic if it satisfies the relation x of t plus t is equal to xt. And in discrete time, if x of n plus some capital N is equal to x of n, this signal is periodic with a time period of n. This signal is periodic with a time period of t. If this equation is not satisfied, this is not a periodic sequence. Okay, then you can also have another classification like even and odd signals. So even odd signal means if x of minus t is equal to x of t, this is even. If x of minus t is minus of xt, this is called as odd signal. Okay, and x of minus t is nothing but the folding operation. You will see that operation when you study the transformations of independent variable. But if you see how you plot xt and x of minus t, if suppose I take this signal as xt, okay, this is minus t by 2 to t by 2. If I fold it, if I plot x of minus t, okay, it means whatever is the portion on the positive side from 0 to t, that will go to the negative side 0 to minus t, and the negative portion will come in the, it is basically folded around this axis, the y-axis. Okay, so this portion will be flipped here, this portion will come here. Now since this is a symmetric signal or even function, you will get the same signal after folding. This is what is the even signal. Okay, and if you might have a signal like this, suppose this is the signal t, this is minus t xt. Okay, and if I fold it, I get it as x of minus t. So after folding, this portion will come here and this portion will go on this side. Now they are not equal. This is not even signal, but if I multiply this with minus 1, okay, if this is x of minus t, that should be equal to minus of xt. What it means, if xt, if I multiply xt with minus sign, it means I am basically reversing its amplitude. Now this multiplication is with your amplitude. This was with time, so this portion will come down negative, the negative portion will go up positive. So minus xt and x of minus t, now they are equal. So this is an odd function or an odd signal. Okay, and similarly in the discrete time, you can say x of minus n is equal to x of n, and x of minus n, if it is equal to minus of x of n, that is a odd function. Okay, Now these classifications, they are not so much important. Okay, you might have studied them in earlier courses, maybe in mathematics or in your basic +2 courses. What was important for us, that was in the last class I have discussed what is building blocks. You have complex exponential signals. Complex exponential signals and sinusoidal signals. So whenever we start with the theory of signals, we always start from this signal because they act as building blocks, and any other signal can be constructed from these signals. Okay. So complex exponentials, we will first define these in the continuous time, and then we will separately define the signals in discrete time, and there are major differences between these signals in continuous time and discrete time. Okay, we'll find out that difference. So continuous time complex exponential is defined as xt is equal to e raised to power j omega t. Okay, and a continuous time sinusoidal signal is defined as xt is equal to a cos of omega t plus phi. This is general representation. Okay, even in this case you can also use this amplitude and the phase factor. You can have like this: xt is equal to a e raised to power j omega t plus phi. Okay, so I am omitting here the phase and the amplitude. So a is your amplitude, a is called amplitude, omega is your frequency, and phi is phase. The units of this frequency is radians per second, and phase is in radians. Okay, for both the cases, omega is your frequency in radians per second. And there is a well-defined relation that omega can be written as 2 pi f, where this capital F is the frequency in hertz or number of cycles per second, which we call as hertz. Okay, so omega can be written in the form of f as 2 pi f. Okay, so this equation, in that case you can modify it as a cos 2 pi ft plus phi. Okay, so if you plot this signal, how it looks like, the sinusoidal signal, you can take sine function as well as cosine function. Both, the difference between them is only phase difference of pi by 2. Okay, otherwise both signals are same. So you have a cosine function. Maybe it looks like this. Okay, so this is, if at t is equal to 0 you are getting the maxima, that is a, it means for this your phase is 0. Okay, so this is just a cos, this is a cos omega t, and phi in this case is 0. This is the one time period. Okay, t, and if your phase is not 0, you will, this maxima will not occur at t is equal to 0, either it will be shifted to the right or left. Okay, so in general you can have a signal like this, maybe. Okay, now at this point, this is for t is equal to 0, this amplitude is not maximum, this will be your a cos of phi, because t is 0, omega t will become 0, but since there is some phase, okay, so at this t is equal to 0, you will get a cos phi, and the maximum magnitude is here. This is a amplitude. Okay, so this you can say is the phase difference phi. Okay, and this will become in that case the time period t. It is periodic signal basically. Okay, now there are some properties of these signals that we will explore, and then when you study the discrete time complex exponentials, you will see how they are different. Okay, I hope you understand this relation omega is equal to 2 pi f, but still I will just revise it. What is this relation omega is equal to 2 pi f? Okay, see, when you say frequency is basically what? Omega is basically number of radians per second. Okay, it means you have a phasor basically. Maybe I take a phasor like this. You have a phasor which is rotating with a frequency of omega radians per second. Okay, and when you get the sine and cosine functions, they are nothing but the projections of this phasor on x and y axis. Okay, you must be aware of that. So if you project this phasor on x-axis, okay, real axis, this is imaginary axis. On this axis, the projection of the phasor on this axis will give rise to the cosine function. The projection of this rotating phasor on y-axis gives rise to the sine function. Okay, so let us suppose we start from t is equal to 0 when the phasor is at this point. So the projection on x-axis is 1, the projection on y-axis is 0. So cosine function will start from 1, your sine function will start from 0. So as this phasor rotates, the magnitude of its x component will start decreasing till we reach at pi by 2. Okay, and at pi by 2 it becomes maximum for your this y component, it becomes 0 for x component. It means the cosine function, it will start from 1, it will start decreasing like this, then it will go like this and so on. Okay, this is t, and this is your xt, which is nothing but cos. Okay, so at t is equal to 0, or this function has maximum value when it reaches pi by 2. Now this point is pi by 2 in terms of phase. If you say angle, this is when omega t becomes pi by 2. This is omega t. If you take it is pi by 2, then at minus pi it becomes maximum, but in the negative direction. Okay, so it becomes at this point, that is minus pi, we are getting minus 1. Then at 3 pi by 2 it becomes again 0, and then at 2 pi, when your omega t is 2 pi, it becomes 1. So this is one complete cycle of cosine function, and similarly you will get here in the sine. The projection of this signal on the x-axis will generate a sine wave. So 0 at pi by 2 maximum, at pi it is 0, at 3 by 2 maximum in the negative direction, that is minus 1, and at 2 pi again 0. This is omega t. Okay, now from this you can get this concept of omega is equal to 2 pi f. Okay, because these frequencies are different. So when this phasor rotates and completes one cycle, okay, when it completes one circle, that is basically one cycle. So corresponding to rotation of one circle of this phasor, you get a corresponding one cycle of the sine and cosine functions. Okay, now what is omega? Omega, we have said it is the number of radians per second. Okay, it means in 1 second how many angles they have been covered. That is basically what is omega. So in one cycle, it covers the angle of 2 pi because it is a complete circle. You have 2 pi radians in one circle. Okay, it means in 1 second, if it covers 3 cycles, okay, that is f, that is number of cycles per second. Suppose it has a frequency of 2 hertz, it means in 1 second it completes 2 circles. Okay, and in one circle you have 2 pi radians, so in 2, how many? It will be simply 4 pi. Okay, so that is how you get this relation, omega is equal to 2 pi f. 2 pi is the number of radians in one cycle, and f is the number of cycles in 1 second. So how many total number of radians? It is nothing but 2 pi f. Okay, so this is what is the concept of frequency in continuous time. Okay, so you have taken a signal xt, which is e raised to power j omega t, or xt is equal to a cos omega t plus phi. We will see that both these signals have the same properties, so that is why we take them side by side. And the first property of this signal is that it is always periodic. Both these signals, they are always periodic with a time period t, which is nothing but 2 pi by omega. Whether you take this signal or you take this signal, both are periodic. And how you can verify it? If this signal is periodic with some time period t, suppose, it means it satisfies this equation, x of t plus capital T should be equal to x of t. It means your e raised to power j omega t plus t should be equal to e raised to power j omega t, or you can say e raised to power j omega small t multiplied with e raised to power j omega capital T should be equal to e raised to power j omega t, and these two sides will be equal only if this factor will become 1. So for this signal to be periodic, e raised to power j omega t must be 1. Okay, so if your e raised to power j omega t, this is capital T, sorry, is equal to 1, what it implies that omega t should be a multiple of 2 pi. Okay, because e raised to power j 2 pi is 1, then e raised to power j 4 pi is 2 pi means cos 2 pi plus sin j sin 2 pi, it is 1, and so on. So t for this is nothing but 2 pi k by omega. And whenever we define the time period t, we take the minimum value of t which satisfies this equation. So when k is 1, okay, when you put k is equal to 0, you get t is equal to 0. Okay, if I put k is equal to 0, e raised to power 0 is again 1. In that case, it becomes a constant signal. So for constant signal, what you can say, sorry, this k can be an integer value. If you have k is equal to 0, okay, your time period will become 0 in that case. Okay, so time period 0, what it means, that its frequency will become infinite because omega will become 2 pi by t. Okay, so t 0 you cannot take because k is equal to, if you put k is equal to 0, even though this equation will be satisfied, okay, but the minimum value of k for which you will get the minimum time period, that will be given by t is equal to 2 pi by omega. Okay, and the same case here, if you see, Again, if you take the same equations, you will get here x of t plus t. That means x is your xt plus t should be equal to x of t. Okay, or simply I simply put this t here. It means it will become a cos of omega t plus capital T. So t plus 2 pi by omega plus phi. It will become again a cos of omega t plus this omega gets cancelled. You will get 2 pi plus phi. You will again get a cos of omega t plus phi, because cos 2 pi plus theta is nothing but cos theta. Okay, so both these signals, they are periodic with a time period that is 2 pi by omega. And if you write omega in terms of f, 2 pi by f, so it is 1 by f. Okay, so either you can use 2 pi by omega or you can use 1 by f to find the time period of the signal. It means if I take a signal like this, xt is equal to e raised to power j 2 pi t, what will be the time period for this? Okay, so I have to simply find what is the omega. Omega in this case is 2 pi. So time period is nothing but 2 pi by omega. 2 pi by 2 pi, it is 1 second. Okay, and similarly if you take x of t is equal to 2 cos of pi t plus suppose pi by 4, what will be the time period? It will be 2 pi by omega. Now you have to compare this with a cos omega t plus phi. So the amplitude in this case is 2, frequency omega is pi, and this is in fact phase pi by 4. So t is equal to 2 pi by pi. You will get 2 as the time period. Okay, and the frequency is 1 by 2 hertz. So if you plot this signal, what you will get, the magnitude is 2 when t is equal to 0. So at 0 you will getting cos of pi by 4. Okay, so it will be not maximum at t is equal to 0 because of this phase. It will be, its maximum will occur at some different point. Okay, and when that will occur, when this argument will become 0, because cos 0 will become 1. It means if I take t is equal to minus 1 by 4, in that case it will become minus pi by 4 plus pi by 4 cos of 0. So at that point you will get 1. So at minus 1 by 4, its maximum will occur, that is 2. Okay, like this. Okay, so this is one time period, and this time period is equal to 2 seconds. Okay, so this is one important property of continuous time complex exponentials and sinusoidals, that they are always periodic with a time period that is given by 2 pi by omega naught, 2 pi by omega. Okay, the second important concept here is that these signals, they are always different. They are always different for different frequencies, means they never repeat. So if you take one signal a cos of 2 pi of 1t and another signal a cos of 2 pi of 2t plus phi, or you can also use it phi, the frequencies are different. It means these signals will be different, they will never match. Okay, so if you take one signal like this, another signal may be like this, although the amplitude may be same and the phase is also same, but the frequencies are different. This is a low frequency, this is f1, this is f2. So this has a higher frequency, f2 is greater than f1. So for any two frequencies, the signals themselves are different, whereas this is not the case in discrete time. Okay, why I am explaining these things? Because when you see in the discrete time, the situation is totally different. When the continuous time sinusoids and exponentials, complex exponentials, they are always periodic, but in discrete time they are not always periodic. First difference that you will see. The second difference that we see, in the continuous time, for different frequencies you get different signals. This is not the case in discrete times. For two different frequencies you may get the same discrete time signal. Okay, so for this case you can say that your frequency omega, it can go from minus to plus infinity. It has infinite frequency range. Okay, because the signals, they never repeat. Okay, and see, when you have a concept of negative frequencies, this is very important. Why we use negative frequencies? Because if you have a real signal, to express a real signal in terms of frequency, you must have a positive and negative rotating phasor. Both phasors you must have. It means you have one phasor which is rotating with some speed in anti-clockwise direction, and one is in the clockwise direction. If you combine them together, you will get a sinusoidal signal. Okay, so if it is rotating in this direction, we say it has a positive frequency. If it is rotating in this direction, it has a negative frequency. It is just the direction of the phasor, nothing else. Otherwise, negative frequency, if you have 1 by 2 hertz frequency and minus 1 by 2 hertz frequency, what it means? 1 by 2 hertz frequency is generated, the sine or cosine function is generated by a phasor which is rotating with that speed in the positive direction, in this direction. Okay, if 1 minus 1 by 2 hertz is the frequency that is generated by a wave which is rotating in the opposite direction. Okay, what it means is that if I say I have a frequency of 1 hertz, or maybe suppose 1 by 2 hertz, suppose positive frequency. Okay, if I plot it maybe in the form of a sine function, so it means my time period is 2 seconds. Okay, so you get a signal like this. This is one time period, and this is 0. This time will be 2 seconds. Okay, this is a frequency of 1 by 2 hertz. Okay, and how you are basically generating it? It is generated from this phasor which is rotating at this frequency in the counterclockwise direction. Okay, so at t is equal to 0, its projection will be 0. Then at t increases, as this vector rotates, you project this phasor on this y-axis and you map that magnitude on here. So when it is pi by 2, you will get the maximum amplitude and so on. This is what I explained in the previous class. Now if you have a negative frequency of minus 1 by 2 hertz, what it means, the time period is again same, that is 2 seconds. You are getting the same sine wave, but it is generated now by this phasor which is rotating in the negative direction. It means that t is equal to 0, it is 0. So as t starts increasing, you are getting first the negative values instead of getting the positive values. So you're getting this wave like this. This is again 2 seconds. We are getting the sine wave, but the magnitude or the amplitude is basically reversed. Okay, where you will get the positive cycle here, at that time you are getting negative cycle here. If it is a negative cycle here, at that time you are getting a positive cycle here. This is what is the negative frequency. Okay, the waveform is same, right? In fact, there is only a phase shift between these two. Okay, and that phase shift is of pi, right? So if we shift this by pi, you will getting this signal. Okay, so negative frequency does not have any physical significance. Okay, but it simply means that the phasor which is generating this sine or cosine function, its direction of rotation is opposite to that of a positive frequency. Okay, so in the phasors, when you analyze frequency in terms of phasors, we use the concept of negative frequency. Okay, so we have discussed two important things in this, that for these two signals xt is equal to e raised to power j omega t and xt is equal to a cos omega t plus phi, they are always periodic with a time period which is 2 pi by omega. Second thing is that the signals themselves are different. You are getting different signals for different frequencies. So based on this, you have infinite frequency range, whether you write in terms of omega or you write in terms of f. So you have a infinite frequency range in continuous time signals. And the third you can say is that as you increase the frequency, as the frequency increases, what will happen? The rate of oscillation, it will start increasing. It means higher frequency signals will have more number of oscillations. Now if you compare these three properties with discrete time complex exponentials, you will get a different picture there. The first difference that you will see that they are not always periodic. The second difference you will see that their frequency range is finite, it is not infinite. And the third difference that you will see that as you increase the rate of oscillation, the frequency does not increase continuously. It will increase up to some frequency, then it will again decrease. It will come to zero frequency, that is DC signal. Okay. So this is what is complex exponential and sinusoidal signals in continuous domain. Now see what is the significance of these. I will just cover why we study these signals first, and then rest of the theory is derived from these signals only. If I define harmonic signals, let us suppose we define harmonic complex exponentials. Okay, harmonic signal means we have a set of signals, suppose skt, which is e raised to power j omega naught at, where k is an integer 0 plus minus 1 plus minus 2 and so on. This is not a one signal, this is a set of signals. We have used the index here k. So you can have s0t, you can have s of 1t, s of 2t and so on. So s of 0t is nothing but e raised to power 0, that is in fact no doubt a constant signal. Okay, s1t is e raised to power j omega naught t when k is 1. Then s2t will be e raised to power j 2 omega naught t, then 3 omega naught t and so on. So what are harmonic signals is that it means all these signals, they have a frequency which is the multiple of a single frequency. This is what is called as harmonic signals. So one signal has a frequency omega naught, another has a frequency 2 omega naught, then 3 omega naught, then 4 omega naught and so on. So if all the signals have a frequency that is the multiple of a single frequency, we call that signal as a harmonic signals. Okay. Now this signal has a time period t1, which is 2 pi by omega naught. This signal has a time period t2, which is 2 pi by 2 omega naught. Okay. Then similarly s of 3t will have a time period 2 pi by 3 omega naught, and so on. In general, the kth component will have a time period of 2 pi by k times omega naught. Okay. Or if I write this time period as t naught, this is nothing but t naught by 2, t naught by 3, and this will become t naught by k. Okay. It means if this signal has a time period of 1 second, this will have a time period of 0.5 second, then so on. Okay. Now if you combine all these signals together, what you get? Okay. If I add all these signals together, because see, this is one thing that you must understand, that if a signal is periodic, suppose I take a periodic signal, and let us suppose its time period is, this is sine wave, 1 second. Okay. If it is periodic with 1 second, I can say it is also periodic with 2 seconds, because it satisfies this equation, x of t plus t is equal to x of t. So t in this case is 1. It means x of t plus 1 will be equal to x of t. But it does also guarantee that x of t plus 2 will also be x of t, isn't it? But when you define the time period, we take the minimum value. Means that if t is the time period, 2t is also the time period. If this signal repeats for this, in place of taking this as 1 cycle, if I take 2 cycles, this will also repeat after 2 cycles. It means whatever is the signal value in the first 2 cycles, the same will be in the next 2 cycles. So if t is the time period, 2t is also the time period. Okay. It means this is t naught. If it means if t naught by 2 is the time period of this signal, this will also repeat after t naught, because multiplied with 2. Okay. So if t naught by k is the time period of kth component, it means this signal will also repeat after t naught. Okay. So all these signals, they have different time periods, but they have a common time period, that is t naught. Every signal will repeat after t naught. Okay. Suppose if this repeats after 1 second, if, okay, so it is t naught. T naught, if you multiply this with 2, you will get t naught. It means it will repeat after 2 seconds. But if it repeats after 1 second, it means it also repeats after 2 seconds. So 2 seconds is the common time period. So if you add all these signals together, what you get, if I add all the signals together, harmonic signals, that is in the form of e raised to power j omega naught kt, k from minus to plus infinity, the output signal that you get xt is nothing but a periodic signal with a time period that will be 2 pi by omega naught. Okay. This is what is basically the Fourier series. Okay. So when you expand in the Fourier series, so what happens if we go in the reverse direction? Means a periodic signal is given to you, and you have to decompose this signal in terms of complex exponentials only. So if you can decompose this signal as a summation of, or as a linear combination of complex exponentials, that becomes your Fourier series. Okay. And in that case, we introduce a coefficient here, ak or ck, which is called as the Fourier series coefficient. And the problem in the Fourier series expansion is now to find this coefficient ak. And this coefficient is generally computed from xt now. So you have xt e raised to power minus, you will derive this equation when you study Fourier series, but I am just saying what is the significance of complex exponentials. Okay. So the Fourier series says that any signal which is periodic in nature that can be expanded in this form. It can be decomposed as a linear combination of harmonic signals. So what you have to simply do is you have to find the Fourier series coefficients using this equation, which is called as inverse Fourier series. So xt is given to you. Omega naught you can calculate by looking at the time period of the signal, and then you have to find the equation for ak. You will find a0, then a1, a minus 1, a2, and so on, and finally put those values here. You will get its Fourier series expansion. Okay, it means any periodic signal that can be decomposed in terms of complex exponentials. And see, in this series now, xt, if I write this Fourier series like this, maybe ak e raised to power j omega naught kt. Okay, summation over k. So this is nothing but a0 constant component plus a1 e raised to power j omega naught t plus then minus side a minus 1 e raised to power minus j omega naught t plus so on. And then finally you can combine these two factors together. If a1 is equal to a of minus 1, you multiply this with 2 and divide with 2, you'll get this as a cos component. If a of 1 is equal to minus of a of minus 1, okay, if they have odd symmetry, in that case in between you are getting minus sign, again you divide with 2j, multiply with 2j, you get a sine function. Okay, so that is a trigonometric Fourier series. Okay, so you can, it means if the signal is periodic in nature, what you can do in the frequency analysis, you can write the signal in terms of sine and cosines only. So that is why the sine and cosine functions or the complex exponentials, they become the building blocks. Okay, because any periodic signal can be composed in terms of complex exponentials or sine and cosine functions, subject to certain conditions that the signal satisfies some properties which we call as Dirichlet conditions. Okay, so it means if you have a square wave, let us suppose you have a square wave like this, a periodic signal. So I can generate this square wave from sine and cosine functions only. And how that basically happens, we are getting different frequencies, and all these frequencies are harmonics. Okay, so if I look at the time period of this signal, maybe this is the time period t naught. So once you have the time period, you can calculate the frequency, fundamental frequency, that is 2 pi by t naught. Then you have to find ak from this signal xt. Once you find ak, you put in this equation, you get its series. Okay, and then you can combine these positive and the negative frequencies to generate sine and cosine components. How it is basically done, suppose you have only first frequency omega naught, now first harmonic, that is same as this. The frequency of first harmonic will be same as the fundamental frequency of this signal. Okay, so you may get a cosine function like this, suppose. Okay, I will just take a notation like this. This is first harmonic. Then you have second harmonic. This will have a double frequency, so it will be compressed in the frequency. Then you have 3 omega naught, 4 omega naught. What happens when you add all these signals together? You get a waveform like this, a close approximation of this original waveform. This may be for 10 harmonics only. If you add more harmonics, if you add 100 harmonics, you will exactly get a square wave. This is how the signal is constructed from sine and cosines. Okay, now what is the significance of this coefficient ak here is that, suppose this is my waveform and I take one more signal like this. Okay, these signals are different in time, but they have suppose the same time period. So how we differentiate them? This can also be generated by sine and cosines, but the sine and cosine that you use for this signal, they will be different from the sine and cosine that you use for these signals, although the frequencies will be same, because the fundamental frequency is omega naught. So all the harmonics will be in the multiples of omega naught, 2 omega naught, 3 omega naught, and so on. but whereas the difference is in this coefficient ak. Okay, so this coefficient will decide basically the shape of the function that you will get. Okay, so this is what is one important significance of this complex exponential signal. That is why we study them, because they form the foundation for any other signals. Okay, and the second important property that we will discuss when we study the linear time invariant systems in detail, but just to introduce the significance of this signal, when you pass a complex exponential signal through a system, a linear time invariant system, you will see that the output of this system is the same complex exponential multiplied with h omega naught. H omega naught is nothing but it is called as the frequency response of the system. So every system has some impulse response which is denoted in time by ht, and if you take its Fourier transform, you get h of omega, which is called as frequency response. So for a purely complex exponential, the output is the same exponential multiplied with the frequency response of the system at that particular frequency. So what it means, if suppose I have a system like this and my frequency response is suppose like this, at a frequency somehow at omega c there is a null point or zero. Now if I pass this signal e raised to power j omega ct through this system, what will be my output? My output will be nothing but zero, because at this particular frequency the response of the system is zero. So this is multiplied with zero, you are getting zero output. This is how the system acts as a filter. When you want to pass or stop a particular frequency, you have to design a system like this, that at that particular frequency the response must be zero. So this is one other important significance of complex exponentials, because when you see we have a periodic signal xt, if I suppose give this signal as input to the system, what is my output? Now first thing is that this signal has infinite number of frequencies. Okay, see, also although this signal is periodic, it has its own frequency, but when you say the frequency analysis, the frequency means a purely complex exponential signal or a sinusoidal signal. Okay, this is what is the frequency analysis. You have, when you decompose the signal in terms of its frequency components, we mean that we are decomposing in sine and the cosine functions. Okay, so if I apply this signal to the system, I want to find the output for any system. So this is an alternate way. What we do, we first decompose the signal in terms of a Fourier series like this, and then using the linearity property, we find the individual outputs. We find what is the output due to the constant signal, what is the output due to this part, what is the output due to this part, and then we add the output, we add them together. Okay, now since we know what is the response of the system for this, it is nothing but the same signal multiplied with the frequency response at omega naught. When you pass a frequency of 2 omega naught, the output is the same frequency, but it is multiplied with the frequency response of the system at 2 omega naught. So this gives you an alternate way to find the output of the system, or you can say it gives you a frequency domain analysis. In time, you cannot see how the frequencies are passed, how the system basically behaves with different frequencies. But if you decompose it in the form of Fourier series, you can see that how the different frequencies are basically processed by this system. So this is another important aspect why we study the complex exponential and the sinusoidal signals. So in the next part, we will discuss its discrete counterpart, that is discrete time, complex exponentials and sinusoids, and what are the differences between them. Okay, and then when you convert a continuous into discrete time signal, how the sampling should be done. Okay, so these are very important aspects that we will discuss next.